Thank you, Sonia, and good morning, everyone. I'm Chloe Fletcher, a senior consultant at Sud Nuclear Technologies. I'm here today to give you a quick overview of the state of the nation in regards to nuclear, hopefully stimulating some talking points for the panelists and during the network sessions lined up throughout the day. In case anyone is new to nuclear, I'm going to start right at the beginning and explain the evolution of reactors over the past couple of decades. So, nuclear reactors are divided into 4 generations. Now, I will note that in the short time that I've been given, I won't be reading out a list of reactors in each generation. So please do bear that in mind if you think I've missed one out. The first generation, this is defined as the first prototypes of nuclear power reactors that launched the availability of civil nuclear power in the 1950s. That gives us 70 years of extensive experience of the full nuclear life cycle, from front-end design through to decommissioning. Some of the reactors, including this generation, are pressurized water, boiling water, and gas-cooled reactors. The second generation refers to the class of commercial reactors that began operation in the late 1960s, based on the first generation technology, but includes CANDU and advanced gas-cooled reactors. Now, the third generation can be split into 2 groups, as shown here on this timeline. But the split is not definitive. Think of it more as a blurred line. Generation 3 nuclear reactors are an evolution of the previous generation, with design improvements in areas such as fuel technology, thermal efficiency, and safety systems, where Generation 3+ are a development of the Generation 3 reactors, offering a significant improvement in safety and modularization capability. Some examples being the advanced CANDU reactor, European pressurized reactor, and small modular reactors. Then finally, the 4th generation of reactors. Now these are innovative designs that have been labeled as having passive safety systems, more economical, proliferation resistant, and sustainable, relating to the minimization of waste. Now, the reason you are all here today is to discuss advanced nuclear technologies. This includes Gen 3+ and Gen 4 technology, as highlighted on this slide. There are 2 acronyms that you will hear a lot today: SMR, small modular reactors, and AMR, advanced modular reactors. You'll hear more detail on SMRs in a later panel, so I will leave that to the experts. For now, I'll explain the family of advanced modular reactors, which encompasses 6 different technologies. The 6 can be shown in the blue box on the left-hand side of this slide. Some are fast reactors, and some are thermal reactors. These reactors can be scaled to be microsystems, small systems, and large systems. However, they all fall into the definition of being able to maximize the amount of off-site factory fabrication, generate low-cost electricity, increase flexibility to deliver electricity to the grid, increase functionality, such as use of heat output for domestic and industrial purposes, and finally, alternate applications that I will also discuss later on. The other distinctive feature of advanced nuclear technologies is modularization. These incur various benefits, such as economies of scale and the shortening of overall build time. However, to benefit from these economies of scale, then manufacturing processes should undergo advancements, such as robotic machining and inspection techniques. Also, module sizes for accessibility to remote locations need to be considered if these reactors are to be transported via roads, especially if these small reactors will be inland rather than by the coast. The primary application of nuclear power is the generation of thermal energy, which we convert into electricity. Advanced nuclear technologies allow for different sizes of reactors, which can support a variety of applications, both on-grid and off-grid. Size of reactors can be defined on the electrical output that they generate. Microreactors are defined as having an output between 1 to 20 megawatts electric. These can be used to access remote locations, but also provide marine propulsion. Although microreactors are already in use in the defense sector, new technologies could provide a valuable alternative to one of the heaviest polluting transport sectors, as shown on the bottom left image. Small reactors are defined as having an output less than 300 megawatts electric and can be used for industrial loads and to access remote locations. And they provide substantially more power to remote locations than a microreactor would. Then large reactors are usually gigawatt-sized. And depending on the type of technology, these can then provide high industrial clean heat that can be used for other applications. And this leads nicely onto this graph on this slide. This graph shows the operating temperatures of different types of nuclear power plants. The orange blocks refer to the existing fleet of nuclear power plants, such as light water and heavy water reactors. The blue blocks refer to the advanced nuclear reactors, such as SMRs, and the 6 types of AMRs. Dark blue referring to the developing fleet, where demonstrator reactors have already been deployed, and light blue referring to the future fleet of reactors. As you can see, all of the 6 advanced modular reactors have high operating temperatures, above 500 degrees C. Now, please keep this graph in mind, as we will be revisiting it to compare against other industrial applications later on. The UK has set itself the challenge of becoming net zero by 2050. This is a challenge that we as a nuclear sector can support through the generation of clean electricity and clean heat, but also supporting other industries to decarbonise. Examples such as the production of aviation synthetic fuel, very apt for where we are now, cement manufacture, ammonia production, and hydrogen production. Now, an expert panel later on this afternoon will discuss the benefits and opportunities within the hydrogen sector. So for now, I will draw your attention to ammonia. Ammonia is used globally as a fertilizer in farming. In fact, around 80% of the world's ammonia is used in farming. With a rise in population, the demand for food will increase, and so the demand for ammonia. Therefore, more development should be placed on the production of green ammonia, which is substantially sourced and could drive down farming's carbon footprint. Ammonia can also be used as a storage medium for the potential use in heating, but also more notably for hydrogen. There are also opportunities for ammonia as fuel for transport using fuel cell technology. As promised, back to this graph now. And those of you still paying attention will notice the addition of the green bars on the top half of the graph. They refer to the operating temperatures for industrial heat processes. This allows us to easily identify which nuclear technologies can benefit from cogeneration applications. It should be noted that all have the capability of generating clean heat for district heating. As I highlighted ammonia earlier, you can see that it operates between 400 to 500 degrees C, which all the advanced modular reactors are operating above. Hydrogen, produced through the more efficient thermochemical method, can be utilised through the high and very high temperature gas reactors and molten salt reactors. However, something to bear in mind is the fact that heat is difficult to transport. Therefore, the reactors designed to produce industrial heat will require to be co-located with the desired process or industrial plant. Nuclear power currently generates 15% of this country's electricity, which is around 6 gigawatts electric, as shown on this timeline. Nuclear has been given the task to increase its capacity to 24 gigawatts electric by 2050. This increase in nuclear capacity is huge. And to complete this in 27 years, then advanced technologies, as those described today, will be needed. The bottom of this timeline shows the reactors that are currently operational, but will be shut down before 2050. Though some of the dates may change due to announcements of life extensions. Currently, only 2 reactors have been announced to be commissioned, Hinkley Point C, as shown on the timeline, and Sizewell C, meaning that we need to commission more reactors to be able to keep our existing capacity, let alone increase it. So based on what advanced nuclear technologies can offer, we should endeavour to support their progress to becoming commercially viable. Each of these points noted on this slide will need to be developed to maturity under a cradle-to-grave approach. I won't go into too much detail on these points, as they will be discussed throughout the panels today, but this slide highlights a few challenges that I will mention before the first panel. Each technology has its own unique challenges, dependent on the environment, but all will consider fuel, coolant, and structural materials. There are both technical and operational skill shortages, so we need to encourage and retain talent in the industry. For a reactor to begin build, it must have a fully licensed site, which could depend on the location of other industries for cogeneration applications. The reactor must have a plan on how to safely decommission with sustainability in mind. This will hopefully give confidence for nuclear to gain more public acceptance on nuclear power plants. And one additional challenge I will mention, but differs for each company here today, is the availability of funds. There are just a few examples that I can only hope that this conference ignites conversations on, and how to tackle challenges that advanced reactors will and are currently facing. So thank you for listening, and I hope that provided some context for today's incredible lineup.